Okay, so this is a pretty complicated problem, but if we kind of break it down into some key things we're looking for, then we're going to be able to kind of understand how to solve this. So first thing you're going to be looking at is that there are molarities. So this is a 0.5 molar HBr, and this is a 0.5 molar KOH. So the first thing I want you to recognize is that you have an acid, because remember I said acids start with H, so you have an acid, HBr, and we're adding it to a base, KOH, and so this is an acid-base combination. So because we know that it's an acid and it's a base, then that's going to tell me that the final delta H needs to be negative, because if you remember at the very beginning of the unit, we said if you have an acid and a base, that's a neutralization reaction, and that's going to make a negative delta H. So that's a good thing to know, is that this is going to equal a negative delta H when we are done. Okay, so that's a good thing to know. Right, now, it says that this is done in a foam cup calorimeter. All right, well, if you do something in a calorimeter, then we know that we're going to use a certain formula, and then that certain formula is this: Q equals MC delta T. All right, so there we go. We now have a formula, and we kind of know a direction. Now, both of these chemicals are at this starting temperature, and they both go to this ending temperature, and it wants to calculate the delta H value. All right, so we got to find delta H for the reaction. Okay, so what we're looking for, and we should at this point write out the reaction, we're looking for this. So it's actually don't want that, I want a pen. It's going to be HBr plus KOH, and that's going to equal KBr plus water. And what we're looking for is the delta H that comes after the formula. So we're looking for that. Now, if you remember, delta H is per mole. And so we're going to have to basically figure out the amount of joules divided by the amount of kilojoules divided by the amount of moles, because delta H is always in kilojoules. So we're going to have to figure this out, kilojoules per mole. All right, so that's what we're looking for. Okay, so let's look at what we have. We're looking for a mass. So that's the first thing we're trying to find. And there aren't any masses in here. We've got some volumes, but we don't have any masses. So there's no masses here. So what the heck are we going to do? Well, if we come down here and we look carefully at the problem, it gave us some hints. They don't usually give us these things for no value. So they said that we can assume that the solutions, I'm going to highlight that right here. We can assume that the solutions are dilute enough to use the specific heat and the density of water. The density of water. They told us that for a reason. Well, they're telling us that there's enough water in these acids and bases that they basically have the same C value as water. And we know that C value is 4.180. But they also said we could use the density of water. Why would they tell us that we could use the density of water? Well, this is why. Density is mass divided by volume. Okay, well, density has a mass. So if we have density and we have volume, we can get mass. Well, the density of water is 1. That's something that you hopefully know. but the density of water is 1. So if I plug in a value of 1 for the density, and it's 1 gram per milliliter, and I'm looking for mass, all I need to know is volume. If I know volume, I can figure out mass. Well, volume is really easy here. We had 100 milliliters over here and 100 milliliters over here. So we had 200 milliliters because basically all of that stuff is in the same calorimeter, right? So it's all in here. So we put in 100 milliliters and we put in another 100 milliliters. And when we do the 100 milliliters and the 100 milliliters, well, then obviously 100 and 100 is 200. There we go. You're going to end up with 200 milliliters in the cup. So we'll put that 200 milliliters right here. And 200 times 1, milliliters cancel. X is going to be 200 grams, or 200.0 grams. So there's our mass. So now we have a mass. So let's correct our arrow a bit there. There we go. Now we got a mass. And a change in temperature. Do we have a change in temperature? Well, yeah, we do. Because we have this, they both started at one temperature. We dumped them in, and they ended at a different temperature. Well, so temperature is going to be final minus initial, which is going to equal final of 23.65 minus initial of 20.29. And that's going to give me my change in temperature. And remember, it's always final minus initial. And so it's going to be a positive 3.36 degrees Celsius. So we can now plug this in and actually get a Q value. Now I want to stress that a Q value is not a delta H value. So a delta H value is not Q, but Q will give us this part right here. It'll give us the kilojoules, the heat part. We'll have to figure out the moles part in a minute. So Q equals the mass, 200 grams, multiplied by the C value. Now you have to remember that this C value is in joules, not kilojoules. So that's important to remember. And I mean, there's more to the unit, but just the joules is the important part. And the change in temperature of 3.36. Okay, so we're going to run this through. This is going to give us a Q value. Okay, so let's get our calculators out. 200 multiplied by 4.180 and enter times 3.36. And we're going to get 2,808.96. Okay, so we're going to write that down. 2,808.96 joules. That's super important. And then if we think about our sig figs, then we've got, let's check our sig figs here. Actually, this should be a 0 here. So it should be 4 sig figs. So we'll call it 2,810 with a decimal like that. But there's 4 sig figs. Good enough. So that's joules. Okay, so let's go back to what we're trying to figure out, and I'll go ahead and circle this again. We're looking for delta H, and delta H is kilojoules per mole. So kilojoules per mole. So we're looking for kilojoules per mole. Well, we have the ability to get kilojoules right here. We just need moles. So that's where we got to go back, and we got to look at this molarity. Half a mole and half a mole. So we have to understand what that means. And so the delta H is per mole. So we have this formula. we have this formula here, which is our acid plus our base. So it's our KBr, which is half a mole, or 1/2 molar, plus our, no, sorry, that's incorrect. It's HBr and KOH. Sorry, my mistake. I was looking at the products. Try that again. HBr plus KOH are going to give us our KBr plus our water. Okay. The problem tells us that you get half a mole of each of these. So this is like 0.5 molarity, 0.5 molarity, which means that you have 0.5 moles per liter. Okay, so what we can do is we can use that to figure out how many moles we have, and so we can then figure out how to find the delta H. Okay, so let's go back to our density formula. Sorry, not our density formula, our molarity formula. So molarity equals moles over liters. Okay, so both of these were 0.5, and they were also both 100 milliliters. So they're both the same exact values. So we can just plug either one we want into this. It doesn't matter because they're the same molarity, same volume. So it doesn't matter. So let's put 0.5 molarity equals X over the 100 milliliters. Now here's the problem. Molarity is dealing in liters. So instead of 100 milliliters, I'm going to divide that by 1,000. I'm going to put 0.100 liters. Now they'll play nice. Okay, so we'll run that through, and X is going to equal our moles. So X is going to equal our 0.05 moles. So 0.05 moles. So you can check that on your calculator if you don't see how to do that. I'm just multiplying 0.5 times 0.100, and that's where I get that 0.05. And I tried to stretch out the sig figs, okay? Now, I'm going to probably run out of time here. So probably going to pause this, and then I'll come back on the next video, and I'll just do a real quick video to show you how to get the delta H, okay? Looking at that, and I have enough time to finish this up. So, okay, so let's go back to what delta H is, and this is really, really good to understand that delta H is kilojoules divided by moles. Well, we have the moles right here. They are right down here. We have 0.05 moles. So 0.05 moles. So delta H is kilojoules for 1 mole, but we don't have 1 mole. We got 0.05 moles, so we have to do a little bit of manipulating. So my delta H is going to be, let's change the pen color. I'm going to put in my kilojoules on top, but that's not kilojoules, that's joules. So we got to divide it by 1,000. So it'd be 2.810 kilojoules over 0.0500 moles, and that's going to give us delta H. So what does delta H equal? Let's run it through real quick. So 2.810 divided by 0.05, that's going to be 56.2. But here's the trick. It's not positive, but negative 56.2. And we know that because at the very beginning we said it was an acid-base reaction, and we said that meant that the delta H would be negative. So you have to kind of understand logically that you've got to apply that negative sign at the end, because it was an acid-base reaction. Also heats up. Things that heat up have a negative delta H. So tough